basics of building science. So as far as references are concerned, building science is a science. Therefore, there is no actual official reference for it. It's no proprietary information of any type. Nonetheless, a great way to read up on building science. A great textbook that's out there. It's Residential Energy, Cost Savings and Comfort for Existing Buildings by John Krieger and Chris Dorsey. You can find these on Amazon. You can find these on the internet at Barnes and Noble, any kind of bookstore. You'll be able to order these particular books. Right now we're in the 6th edition, but nonetheless, building science doesn't really change from edition to edition. It's just they might add additional material to the book. But it's a great reference. I own the copy, and I've always used it for multiple purposes. It's a great book to have handy. So building science, what is it? It's the collection of scientific knowledge that focuses on the analysis and control of the physical phenomena affecting buildings. Traditionally includes the detailed analysis of building materials and building envelope systems. So that is the textbook definition of building science. Now, our overall goal for this is to understand the basics of building science, its principle, application, and how it relates to residential construction. Obviously, there's going to be a difference between residential and commercial, and again, we're going to be focusing primarily on residential in this training. There's going to be 5 sections. We have energy basics, heat transfer, the house as a system, building science and energy efficiency, and then building science and human comfort. So what is energy? Energy is a measurable quantity of heat, work, or light. That's the definition of it. There are 2 main types of energy. You have potential, which is like stored energy, like cord of wood, and you have kinetic energy, which is transitional energy, like a flame. Potential energy always turns into kinetic energy. So for example, the cord of wood, which is potential energy, stored energy, is lit on fire, and it produces a flame, which in that case is kinetic energy. So again, potential energy turns into kinetic energy. Now, while building scientists mainly work with energy related to heat and light, I want to point out that there are many forms of energy that have been defined in addition to the ones listed, such as chemical, nuclear, magnetic, sound, and elastic energy. So just because we're going to be talking about only mainly potential and kinetic, and really mainly talking about heat and light, it doesn't mean that's all there is when it comes to energy. Now, the laws of thermodynamics drive a lot of what we do as building scientists, or just work with building construction and design in general. 2 of the most basic principles in the study of building science are the first 2 laws of thermodynamics, which you see listed here. These laws are fundamental to kind of understand how energy behaves. So you have the first law, thermodynamic. It's an expression of the principle of conservation of energy. So basically it states that energy can be transformed, which means changed from one form to another, but cannot be created or destroyed. So formally, a formal statement about it is basically the increase in the internal energy of a system is equal to the amount of energy added by heating the system minus the amount of lost as a result of the work done by the system on its surroundings. So simply stated, energy is neither created or destroyed. It simply moves about from place to place and changes form from one form to another. So like we talked about earlier, the cord of wood that changes into a flame once it's lit. Now the second law of thermodynamics describes how thermal systems naturally seek equilibrium, and that there's only a finite amount of work that can be done with the specific energy level of a given system. The law states that the heat will always move from one hotter area to a cooler area, so always hot to cold, and the rate of the heat transfer will be based on the difference in the temperature. Heat cannot flow from cooler areas to hotter areas without adding additional energy to the system. So as you can see right here, without an external source. That means that, for example, hot to cold will not reverse without the outside system of, for example, a fan or some kind of other mechanical mean. And that is the law of second law of thermodynamic. The reason that's important is because when we're going to start talking about heat flow into a house, or into or out of the house, I should say, it's important to note that because air always goes from hot to cold, we have to keep that in consideration, whether the hot air is coming from the inside or the outside. So as far as energy goes, there's different ways to measure energy, and different sources of energy are measured with different units of measurement. So for example, electricity, is measured in kilowatt hours. Natural gas is measured in therms. Propane and number two fuel oils are measured in gallons. So each unit of each type of fuel holds a different amount of BTUs, and BTUs can be transferred again to energy that can be produced from that particular fuel source. So again, you don't have to memorize this chart, but this is just to give you an idea of what we just talked about. So on the left hand side, you'll see the fuel type. In the middle column, you'll see the fuel units. So basically the units that that particular fuel is measured in. And then the amount of BTUs that each one of those units holds. And you can see the difference between the four different ones. So we talked about BTUs. What are BTUs? BTU stands for British Thermal Unit. We use the BTUs to measure thermal power and thermal energy. So basically 1 BTU is the amount of energy required to raise 1 pound of water 1 Fahrenheit. And then also 1 BTU is the approximate amount of heat produced by 1 lit match. So if you're wondering how much energy is 1 BTU, it's approximately the energy given out by 1 lit match. So how do we calculate energy? You have power times time equals energy. So this is just to give you a quick example. How much energy is used if you have 100,000 BTUs per hour furnace that runs for 10 hours. So if you again multiply the power, which is the BTUs, so you have 100,000 BTUs times the hours times time, which is 10 hours. You have 100,000 times 10 equals a million BTUs. So a million BTUs will be used by that furnace if it's running for 10 hours. And again, that's being used for a particular furnace for 10 hours, but you can change that power rating and that time to anything to calculate any kind of power usage from any appliance. So let's talk about heat transfer. So there are three basic mechanisms for heat transport. So you have conduction, you have convection, and you have radiation. Conduction is the transport of heat from molecule to molecule through direct contact. This is the type of heat transfer occurring when a pot is heating on an electric stovetop. It is very predictable type of heat flow and is the type of heat transfer that we're trying to reduce when we insulate a wall or a pipe. So the key word to conduction is direct contact. Perfect example, you touching a hot cup of coffee. The heat from the cup of coffee is the heat from the coffee is transferring to the mug, and then the heat from the mug is transferring to your hand through direct contact. Convection is the transfer of heat energy within a moving fluid like water or air. Hot fluids are less dense and rise, cooler fluids are denser and sink. This creates convective flows that transfer heat. So heat that's transferred by moving fluid like air or water, like we said, right? So think of convection in a house. So cold air comes in from the bottom, it heats up, it rises, and then it escapes through the top. So that's an example of convection. And then as far as radiation, it's heat that moves through space from one object to another. So the perfect example of that would be solar radiation. Now heat radiates from the heat body in the same way that light radiates from a light source. The energy radiates in all directions equally, and heat exchange from one body to another that have a line of sight or communication. The heat does not need a medium through which to travel as in conduction or convection. The energy just passes through space or through any clear medium that is not opaque to radiant transmittance. Radiant heat is the heat that you feel from a fire on a cold day. That's another example of radiant heat. Now, standing away from the fire, you're not touching the fire, so there is no conduction. The heated air is rising above the fire. The air around the fire is still cold, but the warmth that emanates from the air through the fire is radiant heat. So when we talk about heat transfer and air movement, we're going to be talking about the thermal boundary and the pressure boundary. They're working in conjunction with one another, but they're two separate things. Okay, so the thermal boundary prevents heat flow between the inside and the outside of the home. And generally speaking, the thermal boundary is the insulation. The pressure boundary prevents airflow between the inside and outside of the home. And generally speaking, it's the interior drywall or the exterior envelope. One thing about the pressure boundary I want to point out, though, is the fact that, like I said, it's usually the interior drywall. That's not always the case. It's a little hard to identify than the thermal boundary, because the thermal boundary, like I said, is the insulation. So you'll see it. That's obvious, right? But the pressure boundary is not necessarily the case. If you have something, and we're going to be covering quality insulation, installation, and pressure boundaries in other sections later. But just to give you an idea, if you have a double wall, the wall that you're looking at from the inside of the house might be drywall, but the pressure boundary actually might be set behind that wall, covered in drywall. So it's not always as obvious as you may think. So depending on the structural complexity of the house, um, the simple drywall that you're seeing from the inside of the house doesn't necessarily mean that is the pressure boundary. The main way to know whether that is the pressure or thermal boundary is that the insulation, as I'm going to talk about in the next slide, always needs to be in full contact with the pressure boundary. So thermal boundary and pressure boundary should always be together. So for maximum efficiency and comfort, the thermal and pressure boundary must be in continuous and in contact with each other. So when thinking of a well-built home, the thermal boundary should always be in contact with the pressure boundary, or in this particular case, as the slide shows it, it's called the air barrier. So when you're thinking air barrier, that's an interchangeable term of pressure boundary. The air barrier is the pressure boundary and vice versa. So the insulation and the air barrier, or pressure boundary, should be in contact with one another all the way around the living envelope of the house, the conditioned area of the house, from the ceiling to the raised floor to the walls, to any kind of soffit and so forth. So that insulation should always be in contact with the air barrier. Here's what happens. If you don't have an air barrier in contact with the thermal boundary, you're either going to get airflow or you're going to get heat flow. And either one of those things is bad when it comes to the comfort and efficiency of the home. So when it comes to thermal boundary, the R value measures the resistance. So insulation is rated in R value, resistance value. So basically, the higher the R value, the more efficient that particular insulation is. The R value of multiple building components can be added together to calculate the composite R value of building components. As I said, the higher R value, the more efficient the insulation is, assuming it's installed correctly, obviously. So the R value measures the efficiency of the insulation. And keep in mind that it measures the efficiency of the insulation assuming that's installed exactly by manufacturer's standards. So you could have a piece of insulation with an extremely high R value, but it's installed improperly or very poorly, and that the actual R value of that insulation is going to be very diminished compared to what it was supposed to be. Now the U factor measures the transmittance or conductance. Keep that in mind. So R value measures resistance, U factor measures transmittance or conductance. The difference between the R value and the U factor is the fact that the R value, as I said, can be added together. So if you have multiple layers of insulation within a boundary, you can add the R values of each one of those layers, and that gives you the aggregate R value for the boundary. Now the U factor cannot be added together. It's not additive in nature, but can be calculated from the R value. So once you find the R value, you can figure out the U factor from it. So the U factor is always the inverse of the R value. So as you can see here on the two little equations, they're very straightforward. So the U factor is 1 divided by the R value. To find out the R value, if you have the U factor, all you do is you invert it. So the R value is equal 1 divided by the U factor. So if you have 1, you're always going to be able to find the other. The lower the U factor, the less heat the material will conduct. So that's also the difference, because they're inverse of one another. The R value, the higher the better. The U factor, the lower the better. So the lower the U factor, the less heat the material will conduct, which is a good thing. For the R value is the higher the R value, the more heat the insulation will be able to stop. Therefore, that's a good thing. Now, the reason we want to know those particular values is because by having those values, we can figure out the heat loss over time. So basically, we're going to be able to calculate how much heat are we going to lose through that particular wall, ceiling, raised floor, whatever it may be, through that exterior boundary over time. And that's important because by doing that, we can calculate exactly how much heating and or cooling we need in the home for it to be efficient and for it to be comfortable. So that is the formula. And the formula is Q equal U, which is the U factor, times A, which is the area of the surface that you're calculating, times delta t. So every time you see a formula that has a little triangle, like so, delta t, delta basically is a difference. The triangle means delta, delta t, and the difference is between the two sides of the surface. So obviously we're measuring the heat loss over time of a surface between the inside of a surface that's dividing an inside and an outside, right? So that difference that it's talking about is talking about the difference in temperature between the inside and the outside. So basically we're going to need to collect the outside temperature and the inside temperature. And then the last piece of the formula is T, and the T stands for time. So we're calculating heat loss over time. So a better way to call this formula would be heat loss over a specific area over time. And again, Q is the heat loss over time, U is the surface U factor, A is the area of the surface. The triangle T is called delta T. That's what the triangle is, like I stated. And that's the difference between the outside and the inside of the surface. And then the T stands for time. So this is an example. So you have a U factor of 0.32. You have a wall that's a 12 by 12 wall. You have the inside temperature is 72 degrees. And you have the outside temperature that's 60 degrees. All you have to do now is plug in those numbers, those variables in the formula that we gave you earlier. So keep in mind that hot always goes to cold, right? So basically in this particular scenario, because the inside temperature is 72 and the outside temperature is 60, this is basically wintertime conditions. So we're going to have, it's going to be cold outside, we're heating up the house. Basically heat is going to be transferred out because the cold is going to be drawing the hot air out, okay? If it was summertime, it would be the opposite. But nonetheless, 72 outside, 60 degrees inside. So the formula is going to be Q equal 0.32, which is the U factor, times 144, which is the calculated area of the wall, which is 12 by 12, right? Times 12. Now that 12, that's the delta T. That's the difference between 60 degrees on the outside and 72 degrees on the inside. That's a 12-degree difference. And that's times 24 hours, which is basically a day. And the result is 13,271 BTUs. So the answer is this particular surface will lose 13,271 BTUs over the course of one day or 24 hours. You got to use this formula in hours. You can't do days. So be sure you use actual number of hours and not number of days. Nonetheless, after you figure out that, you can convert that to days, months, whatever it may be, depending on how big of a time frame you're looking at. But nonetheless, when you're calculating the time, always use number of hours. Don't use days. So that's the answer. So how does that help us whatsoever? Well, if we know that that particular wall, or whatever it may be, it's a wall 12 by 12, we're going to be losing 13,271 BTUs in a 144 square foot area of the house, which is actually not that big of an area. But if you were to calculate that over the overall house, and you were able to know how many BTUs you're losing through the walls, and you're going to be able to bring the number down, now that can help you to size the heating and cooling systems appropriately. Because now you're going to be able to figure out, well, we're losing this many BTUs, our furnace is producing this many BTUs, and you can adjust the gap between the two by doing improvements. Now, when we're talking about the pressure boundary, in addition to the three means of heat flow discussed earlier, a heat flow is also affected by infiltration and exfiltration. And that's where the pressure boundary comes in. So the thermal boundary stops radiation, conduction, and convection. Now, the pressure boundary is going to stop infiltration and exfiltration. So infiltration is uncontrolled air movement to the inside of the home, and exfiltration is uncontrolled air movement to the outside of the home. And keep in mind that the keyword here is uncontrolled, meaning that we're not bringing it in through fresh air means. It's not being filtered. It's not coming in from where we want it to come in or go out from. This is literally air that's coming in or out of the house from random places that we're not even aware of necessarily. Now, air movement within the house, can be calculated in air exchange. So that's a unit of measurement. So it's estimated in cubic feet per minute. 1 CFM of air enters a building for each CFM that escapes. The building is a constant volume. So basically, if you have air leaking in from somewhere, there's an equal amount of air leaking out somewhere else because it's a constant flow. If a home was just going to be pressurized, meaning air was being pumped in and there was no air going out, you blow the roof off the house, right? Again, in the opposite end of the spectrum, if there was only air going out but no air coming in, you'd be depressurizing the house to the point where it would implode, right? Obviously, those are extreme scenarios. Just to kind of visualize what I'm talking about, you're never going to have a house that implodes or explodes due to air movement, but that's what I'm talking about. It's a constant air movement volume. In order for air movement to occur, three things need to be present. You have to have a hole, you have to have a pressure difference, and you have to have an amount of air. Those are the three things that have to be in place. Obviously, you have to have a hole, to go, a place for air to go in and out of. You must have a pressure difference, meaning the pressure differences drive air movement. So for the most part, air movement goes from high pressure to low pressure. So that means the bigger the difference in pressure between the two areas, the more air movement you're going to have. If there is no difference in pressure, there is not going to be air movement because there's going to be nothing driving air movement from one place to the other. And then obviously you have to have an amount of air, any amount of air. So when it comes to air movement in relation to building design and building operations, stack effect is directly related to that. Okay, so warm air rises and leaves the home through the holes near the ceiling. Cold air enters near the floor to replace it. So basically you have cold air, which is denser and comes in from the bottom. It's being sucked in at the bottom of the house. This could be the case also in a single story home, by the way. It doesn't mean that it has to be a multiple story home for this to work. But the reality is the fact that the higher the building, the more stack effect is going to be present in that particular home. But nonetheless, you could have the stack effect also be present in a single story house. Nonetheless, cold air enters the bottom of the building. We're going to have negative pressure. It rises, it pushes up, and then because the air is being pushed up to the top, you're going to have more positive pressure toward the top of the building. And that air is going to be pushed out through exfiltration points somewhere at the top of the building. And that's an example of stack effect. Now, given the fact that that's a constant airflow, it's uncontrolled constant airflow, what that's going to happen is that's going to create a convection loop within the actual house. So as air is being pressurized, as air is being heated and rising to the top, it's going to be sucking cold air from the bottom. So it becomes almost a vacuum effect within the home itself that perpetually keeps the convection loop going. So hot air pushes up, sucks cold air from the bottom, and it just keeps going. Now, wind pressure is another way that the home can be affected. And the pressure boundary is obviously related to it. So the pressure builds up on the side of the house facing upwind, and then the pressure is released through exfiltration on the side of the house facing downwind. So as you can see in the picture, you have wind that's pushing on the left side of the house, and that's the wind direction, right? So it's putting positive pressure on the left side of the house. Through infiltration points, air is going to leak into the house, and it's going to push through to the right side of the house, creating positive pressure. And that is going to get sucked out from the outside, again, because that's the wind direction that it's going. And then on top of that, because you have wind that's being pushed all around the house, it's going to create a wind tunnel around the house as well. And the wind tunnel is going to pull the cold air from the right side of the house as well. And again, it's going to perpetually going until we stop it by creating a proper pressure boundary. One less way for air to go in or out of the house is the mechanical effect. Now in this particular scenario, this is not considered infiltration or exfiltration because it is controlled air movement. As I said earlier, the key word for infiltration or exfiltration was uncontrolled. So this is controlled because you actually have a mechanical system that is pulling or pushing air in or out of the house at preset times in pre-designated locations and so forth. So mechanical effect is not considered infiltration or exfiltration, but when we're talking about heat transfer, and air movement, nonetheless, this has to be part of the conversation. In addition to that, mechanical effect can cause other problems, which we'll talk about in a minute. and that will be covering the house as a system. So what is a system? A system is a set of interacting or interdependent components forming an integrated whole. A system has three things. So it has a structure, which contains parts or components that are directly or indirectly related to each other. It has a behavior, which contains processes that transforms into inputs into outputs. So in our particular scenario, for example, energy, right? And they have interconnectivity. So the parts and processes are connected by structural and or behavioral relationships. So basically, each building component in a house interacts in some way with the other building components within that particular structure. So what are the building components of the house? We have the building envelope, space conditioning, lighting and appliances, mechanical ventilation, water heating and distribution, and obviously the occupants as well. Homeowner behavior will interact differently with how the other components of the house itself and how they were built. So the house is a system made up of interdependent parts, which I just listed a second ago. The operation of one part affects many others. So for example, the insulation and the quality of the insulation will affect how the air conditioning system works. Poor insulation will make the system work harder, for example, right? That's a very easy example. When all parts work together, the house is comfortable, safe, efficient, and durable. A house will experience problems when its components do not work in unison. So the problems that can arise from components in a house that don't work properly together can range from just high energy bills. They can result in just inefficiency, discomfort, and in some scenarios can also produce life-threatening scenarios, which we'll talk about in a minute. So for example, let's talk about some interconnectivity issues, right? So an attic without insulation makes the heating and cooling system work harder than necessary. So this will decrease the HVAC equipment's life and cause higher than necessary energy bills. So let's say in the winter, again, you're heating up your house, there is no insulation in the attic, that hot air will just rise up and it will leak out, right? It will transfer right out. So your heating system will work probably twice as hard as it should. Therefore, your energy bill is going to be higher. The life of your equipment is not going to be as long as it should because it's going to be working much harder than it's supposed to. So that's an example of two systems not working properly together. Another example, you have leaky recessed lighting fixtures, and you see pictures here with thermal camera. Increase heat loss and gain. So please note on the right hand side, the hot roof in the picture on the right, the hot air rising through leaks around the candlelight deposits in the attic. Again, so that goes with heat losses, right? So the heat inside the house is leaking through the poorly sealed can lights, and it's heating up in the attic. So you can see in the picture on the right hand side, you'll see the roof that's bright red, right? So that means that the attic is hot. So assuming that's a non-lived in attic, that attic should be cold because it should be completely insulated from the inside of the house. This is an example of mechanical ventilation not exhausting properly to the outdoors, which can cause moisture damage to the roof deck and trusses. So moisture in this particular case will deposit and condense on the underside of the roof, causing it to rot over time. So basically, you have any kind of mechanical ventilation exhausting from the house, and it needs to exhaust completely outside of the structure, not just into the attic. So basically, in this particular scenario, you have mechanical ventilation that's exhausting hot air from the inside of the house. Now think of the fact that the attic is going to be colder, right? So as hot air reaches the cold attic, the hot air is going to condense, and moisture is going to form in the area around that vent in the attic. And that moisture eventually is going to be absorbed by the building materials, and it's going to create rot and moisture problems down the line. So those are just examples of it, but basically everything in the house interacts with one another. So you can't insulate unless you air seal, right? So because air sealing is basically pressure boundary, insulation is thermal boundary, like we mentioned earlier. If you insulate without air seal, you don't have the pressure boundary, thermal boundary connection, so you cannot do one without the other. You can't air seal unless you insulate. If you stop the pressure boundary, but you don't put a thermal boundary in there, now you stopped air movement, but now you're not going to stop heat flow, right? You can't air seal unless you have combustion air. So combustion air is basically the air necessary for a combustion appliance to burn properly. If you air seal but don't provide any kind of makeup air for your combustion appliances are not going to work properly and they're going to create CO, which is a dangerous chemical, which we'll talk about in a sec. And then you have to test for combustion after you air seal. So every time you air seal a house and you basically tighten it up, the pressure boundary of the house is now much tighter. There's the potential of a dangerous situation being created with your combustion appliances. So it's important that you test for combustion air after air seal. So basically you have to make sure that there's enough makeup air for those combustion appliances to work properly. Now, as you can see, everything works with one another. You cannot do each one of these things interdependently. You have to take everything else into account. If you don't, again, you might have energy problems, you might have comfort problems, you might create actual damage to your structure due to moisture and so forth, or you could create dangerous situations just like the production of CO, which can kill you. So when, like I said, when the house does not work as a system, problems will occur. Insulating and venting the attic without air sealing could damage the roof, like we mentioned. Air sealing without insulation could cause moisture problems. Air sealing and insulating without attention to the HVAC ducts will not reduce duct leakage. So for example, you air seal and insulate your walls, but now your ducts are still leaking like a sieve. Obviously, that's still going to be very inefficient. And then air sealing without combustion safety testing will cause a hazardous and potentially fatal situation for the residents. Not knowing the status of the air tightness of the house in relation to the combustion appliance present, it's a danger on its own. So it's not necessarily that it's going to happen, but the reality of the fact is that it might happen. And not knowing whether it does or not is dangerous on its own. Anytime you air seal, you absolutely should test the house to make sure that the combustion appliances are working properly with the new air sealing. And these are additional examples. So insulating and venting an attic without air sealing could cause moisture damage on the roof. So if you're not air sealing, it means that you're stopping heat transfer, but not air movement. So the hot air rising from the house will condense and potentially freeze on the underside of the roof, causing damage to the roof and allow moisture to fall back on the insulation and below. So you have hot air that rises in the attic. Once it touches the cold roof deck, it condenses. Therefore, once it condenses, it might freeze depending on the temperature on the outside. Eventually, it'll melt. It'll cause damage to the roof deck, plus that moisture will fall back on the insulation. So it's a chain reaction effect that can cause multiple problems. Also, keep in mind that the problems that you may encounter vary from climate zone to climate zone. So the problems you're going to encounter in a hot climate zone are going to be different than the problems you encounter in a cold climate zone. So another example, air sealing without insulating could cause moisture damage. So heat transfer will cause condensation to build within the walls once the outside air touches the inside surface, or vice versa, thus causing moisture to form in the wall cavity or on the walls. So basically, you have a wall that's properly sealed for air movement, but there is no insulation in there. So what's going to happen is you're still going to have heat transfer coming in from the outside or the inside, depending on what's going on. And because there is nowhere for that air to go, because it's sealed, that air is going to be trapped within the cavity. And due to the temperature differences, it might condensate. If it condensates and becomes actually moisture, then at that point it'll deposit on the inside of the walls and start causing moisture problems from the inside out. And as you can see here, it's an example of a wall that's rotting and there was moisture being built, could be from the inside, due to that. Air sealing and insulating without attention to the HVAC will not reduce duct leakage. So obviously improving the thermal and pressure boundaries of a home will not solve the energy loss associated with the leakage of the HVAC ducts and the moisture problems associated with it. So again, you could have a perfectly built house on the outside as far as the walls, ceiling, raised floor, and then you have an air conditioning system that's leaking completely. And basically if it's leaking, it's going to be sucking air in or out of the outside of the home because that's where the ducts most likely will be. So you got to also pay attention to the duct sealing on top of that. Air sealing without combustion safety testing, that can potentially kill somebody. So like I mentioned earlier, air sealing may cause combustion appliances not to vent properly, thus causing backdrafting and forcing CO inside the house rather than letting it flow outside. CO is a very dangerous chemical and it can kill somebody. So that's what CO is. So it's a colorless, odorless, tasteless gas. It's highly toxic. It's a byproduct of improper combustion. So if combustion appliances don't have enough oxygen to breathe properly, they produce CO. And CO can cause a range of symptoms depending on exposure levels, for anywhere from a headache all the way to death. So if there's CO exposure within the home, a lot of the low-level exposures of CO are actually flu-like symptoms. Now you cannot smell CO, you cannot see CO, you cannot taste CO. So a lot of times you might be in a dangerous situation where you think that you might just have a flu or you just don't feel good, but the reality of it is the fact that you're breathing in CO because your home is not performing properly. So if the house is very airtight and there is nowhere for CO to draft out, or it's being drafted inside because mechanical ventilation is sucking it in from the appliance, they can cause a very dangerous situations. If you read in the news or if you do research, you'll see that around the winter seasons, thousands of people die yearly from CO exposure. It's a very common thing to happen, and it's something that you definitely have to be aware of when performing modifications to the house. Energy and efficiency can be divided into the following general categories. You have heating and cooling. Seasonal efficiency for fossil fuel heating systems range anywhere between 30 to 90%. Most older systems operate at the mid to lower level of the scale. You have air leakages, so infiltrating air must be heated or cooled to a comfortable temperature, and heated or cooled air is lost when air leaks out of the building. You have water heating. Energy losses in heating and storage of hot water can amount up to 40% or so of the system energy consumption. You have appliances and lighting. So refrigerator, lights, entertainment systems, computers, and other appliances, they use considerable electrical energy because of obsolete design, careless operation, or just the sheer number of electrical devices in a home. Think of a number of laptops, tablets, phones, computers, TVs, gaming systems. All those add energy usage to the home. And think of how many electronics we have added to our average homes compared to where we were 10, 20 years ago. And then finally, you have residential behavior. The awareness and care of building residents and managers has a significant influence on how much energy the building uses. So aside from actual, electronics and building design, I mean, the homeowner has a very big impact on the efficiency of the home. If a homeowner leaves all the lights on all the time, obviously they're going to be using a much more they're going to be having a much higher energy bill than somebody who doesn't. So generally speaking, typical residential buildings use 1.5 to 2 times more energy than necessary, and that's through a combination of the things that I just listed a second ago. Largely, though, is caused by lack of insulation, infiltration, and improperly installed or inefficient heating and cooling systems. So this excess energy usage costs about $45 billion annually to the U.S. So think of all that energy and efficiency and how much that translates to 45 billion. That's quite a number. So achieving maximum energy efficiency can be reached through the use of two methods, and these are the ones that we're going to be talking about. We have energy efficiency strategies, which is using devices that draw less energy, often resulting in energy savings. And then you have energy conservation strategies, changing individual habits to reduce energy use. So energy efficiency is the more popular approach and focuses on maximizing the economic benefits of wise energy use. Energy efficiency often results in energy savings, as when you buy a new energy efficiency star qualified refrigerator to replace your inefficient old one. So basically, energy efficiency strategies really have to do with improvements of the home. Now, energy conservation focuses more narrowly on reducing now renewable energy use and its resulting environmental damage. Proponents of this approach are more willing to ask consumers for changes in behavior than than the energy efficiency approach. So energy conservation is more behavior focused versus the energy efficiency, which is more building component upgrade focused. So these are examples of energy efficiency strategies. So making thermal improvements to the shell, replacing older heating and cooling systems with newer, more efficient ones, installing smart strips to appliances, or replacing incandescent light bulbs with CFLs or LEDs. Now, as far as conservation strategies, these are other examples. Unplugging appliances when not in use, not cooking during the heat of the day, using clotheslines instead of dryers, or programming the thermostat properly so that it's preset at certain temperatures and times. So again, you can see these are more behavior-based versus upgrade-based that we saw in energy efficiency strategies. So how does building science relate to actual human comfort? Now, there are different factors that determine personal comfort. You have air temperature, you have relative humidity, you have air movement, you have mean radiant temperature, and then you also have the individual itself. Now, we mentioned a second ago air temperature, and we talked about, well, I mentioned relative humidity. So those are examples of sensible and latent heat. So what do they mean? Heat obviously has to do with personal comfort. It's a big factor in it. So sensible heat, it's heat that causes a change in temperature in an object. So that's a very easy example of air temperature, right? Latent heat is heat that causes a change of state, like solid to liquid or liquid to vapor, with no actual change in temperature. So relative humidity is an example of latent heat. So we talked about air temperature. So basically, it's very easy to measure with a thermometer, for example, right? It's the measure of how hot or cold the air is. It describes the kinetic energy of the gases that make up air. And as the temperature increases, air molecules move more quickly. As it decreases, they slow down. Hence, they turn into a vapor or they condense down to moisture and then down to a liquid. Now, relative humidity is the ratio of amount of water in the air relative to the amount of water that air can hold in its current temperature. So warm air can carry more moisture than cold air because it becomes less dense when heated. So as it becomes less dense, the molecules expand, hence allowing it to hold more moisture. So 100% relative humidity is completely saturated air. So at 100% relative humidity, it's basically raining, right? That's what 100% relative humidity is. Healthy levels are between 40 and 60%. And this is the chart that shows that. So when it comes to humidity, there is health factors and problems that can vary whether it's too dry or it's too moist. And you can see here the range of what those problems may be depending on the range of relative humidity. And as you can see, the safe zone or the hot spot, I guess, is between 40 and 60. That's the healthy range. You're still going to have some problems about some of these items in that range, but nonetheless, they're going to be greatly minimized. The lower or higher you go, the more those problems are going to manifest themselves. And this chart shows the perceived temperature due to relative humidity. So if you have a low temperature, but nonetheless you have high humidity, it's going to feel hotter to the individual than it actually is. So in this particular scenario, I'm just going to use an example. If you look at the column that says 80 Fahrenheit for air temperature, but then you have 70% humidity, now it's going to feel like 85 degrees to the actual individual. And that's how it works. Because of the fact that the temperature is higher, therefore it can hold more moisture. The relative humidity might be higher, and it's going to give a perception of a higher temperature, therefore decreasing the comfort of the individual. So air movement can increase heat loss without any change in actual temperature. So it does increase personal convective heat losses. If the air temperature is less than the skin temperature, it will significantly increase those convective losses. This occurs because more air is coming in contact with the warm skin as it blows past. With little or no air movement, now mean radiant temperature, the measure of the average temperature of all the objects in a space, including the walls, windows, furniture, and people. So it's critical to human comfort because our bodies radiate heat toward cold surrounding surfaces and receive heat from hot surrounding surfaces. So there's about 1 degree change in mean radiant temperature is approximate to 1.5 degrees change in air temperature. So our surroundings affect our comfort level. And then, of course, the individual. The individual will have an effect on its own comfort based on the physical condition of the individual, the level of activity of the lifestyle, the age, the metabolism, the acclimation, and the gender. So basically, any of these items will affect the comfort of the individual independently from everything else that we just talked about. So everything else could be proper, but these factors will additionally change the comfort of the person. And again, if you have any questions, contact us through the messaging system or give us a call.